Okay, good. Okay, good morning, everyone. I'd like to welcome you to this morning's workshop, Age Period Cohort Analysis in Population and Health Research. My name is Brady West. I'm the director of the Scientific and Technical Core within the Population Dynamics and Health Program, which is sponsoring this morning's workshop. So we wanted to get started just by saying a few words about PDHP, and then we'll get into more of the logistics about today's workshop. But very happy to have everyone here, those of you in the room in Ann Arbor, also those of you joining online, welcome and very happy to have you here. So the Population Dynamics and Health Program is a research infrastructure program that's located within the Population Studies Center here at the Institute for Social Research at the University of Michigan, Ann Arbor. PSC primarily focuses on population research and training of graduate students and postdocs who are doing work in the population sciences. The Population Dynamics and Health Program itself is funded by the National Institute of Child Health and Human Development via a P2C grant. So we're very thankful for that support, which makes workshops like this possible. Within the PDHP, we have a focus on supporting projects that are funded by the Population Dynamics branch within NICHD. And that includes many substantive areas related to families, children, and demography. So today's workshop fits squarely within that area of research support. We also have a heavy focus on the development of junior faculty, so it's good to see a lot of junior folks here and online today. And PDHP also supports the development of new proposals that are going into the Population Dynamics branch. As I mentioned, I'm the director of the Scientific and Technical Core within this Population Dynamics and Health Program. We provide scientific and technical guidance and support for a variety of aspects of the research enterprise. Could include statistical methods, could include computing, working with restricted data sources, consultation on programming and support for programming, also data science techniques, including data linkage and visualization. You can sign up to be an affiliate of the Population Dynamics and Health Program if you're not already, and affiliates receive the ability to have free consulting with the Scientific and Technical Core on any of those aspects that I just described. STC staff are also willing to enter into subcontract arrangements if you have funded research projects and you need help with data management or data analysis or some aspect of research methodology. We'd be more than happy to speak to you about the possibility of entering into these subcontract arrangements. So you've all heard from Paul Schultz. Paul is our lead data scientist and statistician working within the PDHP, and our other staff as well would be helping with those kinds of subcontract arrangements. So please don't hesitate to let us know if you'd be interested. PDHP staff also help out with coder spaces within ISR. So again, if you need assistance with programming, we'd be more than happy to meet with you there. And the PDHP also puts on workshops like the one that we're here for today. So very happy to have everyone here today. I want to mention as well, I have the PDHP website displayed where you can find more information about the activities of PDHP and some of our different events and activities. We also have a YouTube series where you can see recordings of prior PDHP workshops. So I've highlighted that here up on the screen. So you can kind of scroll through this list if you go to the PDHP website, and you'll find a lot of the different topics that we've given previous workshops on. Those are all in the public domain. So if you'd like to check out any of those YouTube recordings, I think we've offered a lot of interesting stuff over the years. So you can find a lot of good stuff on research methodology there. Again, all in the public domain. So any questions about PDHP, again, feel free to reach out to Paul or myself. We'd be more than happy to talk to you about some of these opportunities and events. So without any further ado, it's truly our pleasure to have Dr. Claire Yang here today. She goes by Claire, but I'm going to refer to her as Dr. Yang in her introduction here. Dr. Yang is the Ellen Shapiro Distinguished Professor at the Department of Sociology in the Lineberger Comprehensive Cancer Center. And she's a fellow of the Carolina Population Center and the Carolina Center for Population, Aging, and Health, all at the University of North Carolina at Chapel Hill. She's a demographer, medical sociologist, and social statistician interested in population health, aging, and the life course, and quantitative methodology. She has extensive expertise on the demography and social biology of aging and health, and new statistical methodologies of cohort analysis for interdisciplinary population health sciences. Her recent NIA-funded research brought integrative biosocial theoretical perspectives to bear on the analysis of diverse forms of big health data and revealed new knowledge about social disparities and underlying biological mechanisms in chronic diseases of aging. Her current research focuses on innovative methodologies of complex, coordinated, and integrative data analysis of multiple longitudinal cohort studies. She and her team recently employed novel integrative data and methods to model cognitive aging across the full lifespan, reveal early and midlife social disadvantages that are associated with cognitive declines with aging, and explicate the biological pathways linking social disadvantages with cognitive impairment over the life course. So again, very happy to have Dr. Yang here with us in person today. Okay, so without any further ado, we're going to turn it over to her slides and we'll get the workshop going. Just some logistics, those of you online, if you have any questions, feel free to enter them in the chat. Paul's going to be monitoring chat messages and he'll relay those back to the room here in Ann Arbor. If you're in the room and you have questions, feel free to raise your hand or speak up and we'd be more than happy to address those. Okay? Okay, so we'll turn it over to Dr. Yang's slides. And again, thank you.
Can everyone hear me okay in the back of the room? Thank you. Thank you so much, Brady, for the nice introduction. It's my pleasure to come back, revisit ISR and this beautiful campus. One of the, ISR is one of the most renowned Institute of Social and Population Sciences in the country. And I'm also very delighted to learn about PDHP and give this workshop on a very interesting and sometimes controversial topic. So a little bit of background before I begin. So I teach a graduate seminar on this precise topic semester long, and actually just this past spring semester, I taught this course. And so in order to prepare for this workshop, I condensed the main points of the semester long, graduate seminar into this 4-hour session, and so it's been a little challenging because a lot of things are important. I somehow can't include them all. But the challenge for you is also to take it all in this short time period. But don't worry, we'll rally. So let me get going with the slides here. So before I begin, I want to kick off with this, sort of key motivating question. So why we're doing what we're doing here. An essential question of interest to population and health research is how do we make sense of change, particularly time-related change. So for example, if you ask 3 different people to tell their life stories, you will hear 3 very different tales. And they will likely reflect on how times have changed and how this has made their lives different from the lives of their grandparents, their parents, and perhaps their children. Right? So comparing lives and time is one of the ways in which we all make sense of time-related change. So this is a course that helps you to conduct quantitative studies of time-related change, namely those associated with the aging process, those associated with historical time period, and those associated with birth cohort membership. So why is this question important? Well, this whole workshop is talking about that. So essentially, just to summarize, there are many reasons why we may be interested in the effects of being in a particular age group, being in a particular birth cohort, and it being in a particular historical time. And so, and all of these things have strong bearings on population health trends. So all of these factors may be working simultaneously or to affect the outcomes of interest, or they may act independently, and which factors may be more important than others may sometimes be of interest as well. So how do we address this scientifically? So most population and health research deals with temporally ordered data, if you think about it that way. So by that I mean population or survey data that are organized in the form of observations that are repeated over or ordered along a certain time dimension. So to study change, time-related change, we compare these data recorded at different points in time, oftentimes age-specific data recorded along, for different birth cohorts along different times. So a systematic study of such data is termed age period cohort or APC analysis, which sometimes synonymously is also called cohort analysis, and I'll explain why that is the case in a few minutes. So it is interesting because it has this unique ability to provide a parsimonious summary of the entire complex of social, historical, and environmental factors that simultaneously affect individuals. So it has been widely used in studies of epidemiology, demography, and aging. So this is my favorite example to give to illustrate all the points I've just mentioned. So the topic, the question is, and what do you think? Are millennials killing the joint replacement industry? I'll give you a couple minutes to stare at the graph, right? We laugh, right? So it's looking at baby boomers. We all know who they are. Those who were born in 1946 and 1964. If, say, in 2020, they're in the age range of what? 65 and above, just generally, not to do math so early in the morning. Millennials, when were they born? Millennials refer to those born 1981 to 1996. So in year 2020, they'd be in what age range? 25 to 40. It's too early for math. It's okay. So anyhow, that doesn't take your attention away from this graph. So what's going on here? What's wrong? Are they, what's your answer? Are they killing the joint replacement industry? No, they're not. What is wrong with this whole thing? All right. I already asked you to do the math. So basically what I'm getting at is that this is a typical mistake that people make when they mix up cohort effects with age effects. It's not the cohorts per se, the millennials that are ruining the joint replacement industry, but because of the age-related impacts that younger age compared to older age have much lower rates of disability, right? So this is a course that, that teach you how to disentangle these different sources of temporal changes and address it scientifically. So here's a overview of the plan for today, and let's hope that we can carry it over, through both the prepared and structured stuff as well as some interaction. So I will provide a broad overview of key methodological issues in APC analysis with introduction of various tools available and how you might, the analysts might choose among them. And there are, after the introduction, I will talk about 4 topics. And each topic includes a combination of overview of key theoretical background and principles, illustrations of prototypical data sets within each research design, as well as models and methods for analyzing such data. And I will also give examples of data analysis using these methods, and as well as the sample codes using various statistical software. And so, my plan is to go through the first topic, until 10, and then we'll have a 15-minute break to go on with the rest of the topics, with breaks in between each topic. And then I will also leave about 5 minutes time toward the end of the section, hopefully for Q&R. Some of the Q&Rs probably will also sort of leak into the 15-minute break. We'll see how we feel at that time. Is this plan sounding okay for everybody? All right. So let me then also just briefly talk about my goals today. So I hope this workshop can help you, enable you to do 2 things not possible before. First is to learn to use the most up-to-date innovative estimation methods and new models to conduct APC analysis. There's this stubborn problem called identification problem in conventional APC analysis. Hopefully by the end of the workshop today, you will feel that you will have a good handle on how to deal with that. And second, more importantly, is that I hope to, you can use APC analysis in more flexible and broad ways to expand its utility to investigate deeper mechanistic kind of questions, or to advance mechanistic knowledge about the temporal dynamics and temporal context of any phenomena of interest to you in population and health research. And so this is the outline for the intro, the topics I want to cover. So first I want to sort of, again, briefly introduce why we care. Why is APC analysis useful? So we first must understand what they stand for, what these effects mean. And so I will give some conceptualizations of these time-related variables, followed by their utility. And then we'll also look at some of the problems of distinguishing these effects in actual analysis. And then I will talk about 4 study designs that enable us to conduct APC analysis with temporally ordered data. We'll look at the general data structure that suggests different modeling strategies and also help us with data preparations. I will give examples of specific data sets typical for each design that will be used in subsequent sections to show how to work with them to implement various methods. So for those of you who have taken tomography or are familiar with the Lexis diagram, this should be relatively fun, but it's okay if you haven't. So I have translated the diagram into a visual presentation of the 3 different dimensions of time and how they are different but also related to each other. So this is a visual depiction of the 3 time dimensions. So in this example, you see the horizontal line, 1, 2, and 3, 1, 2, and 3, that represent 3 individual age trajectories for cohorts born at the beginning, at the middle, and toward the end of the 20th century. Right, so they all, so the timeline is also marked by major historical events from Great Depression to Civil Rights Movement to Internet to COVID-19. So these 3 different lifelines, trajectories for cohorts born at different times went through these historical events at different time, at different points in life. So this shows that there are clearly, very distinct meanings of these time dimensions, but they somehow also intertwine with each other. So based on this, oh, what did I do? Okay. We then would want to give them their formal definitions in the context of population health research. Right, so age effects are simply variations associated with chronological age that can arise from internal changes through physiological changes, accumulation of social experience, sometimes say when one matures, that's what we mean, and social role and status changes, or a combination of all these things that reflect both biological and social processes of aging, internal, endogenous to individuals that represent developmental changes across the life course. And they can be readily observed with considerable regularities across time, space, and even species. And so they are of particular interest to population research in where age variations are the most common, most important source of change in disease and vital rates, fertility, mortality. You can see pretty strong regularities across time, space, and species. On the other hand, period effects, they are variations over time periods or calendar year that influence all individuals alive. So they subsume a complex set of historical events, environmental factors such as wars, famines, technology changes, economic expansions and contractions, and they're often evident from a correspondence in timing of changes in the outcomes and conditions inducing these outcomes. And they can also, this is a special case in health research, is that where they can also be observed from changes in disease classification or diagnostic techniques. And a prominent example of the increasing diagnosis and incidence of breast cancer in recent decades for women. So still a third, cohort effects. The applicability of APC analysis really relies on the substantive importance of cohort influences. So in the absence of cohort influences, there's really no point of having to do this. So in this way, in this sense, APC analysis is synonymous with cohort analysis. So cohort effects are then defined as changes across groups of individuals who experience an initial event in the same years. The event oftentimes are birth, but it does not have to be birth. And then APC analysis is particularly referring to birth, defines the cohort. So when this is the case, when the cohort is defined by birth, cohort succession, replacement of each cohort across time is then set to drive social change, and it's also termed as underlying what's called demographic metabolism. Inflow into the population through fertility and exit the population through mortality. So they reflect something different from both age and period effects. They reflect early life conditions and also lifelong continuous exposures to social, economic, behavioral, and biological risk factors. So in this case, the sociological theories advance this principle of cohort differences in aging that talks about how birth cohorts contextualize individual aging process. It can, shape individual specific trajectories of aging. So as an example of how, the importance of cohort trends in population health, this is a famous article done by Finch and Crimmins, published in Science, that documented large continuous cohort declines in human mortality. These are from the Human Mortality Archive from Sweden, the best mortality data recorded to date for human populations, where they have shown how cohort-specific, age-specific mortality by cohorts have experienced continuous declines from cohorts born in the 1700s to 1940, where there could be up to 100-fold decrease in age-specific mortality rates across cohorts. And so this is, sort of one example of how, cohort trends are important for population health, which then naturally leads to why, is this useful? Why the utilities of APC analysis? So first, it is crucial for attributions of etiology or social causation, right? So in the age effects represent age-related developmental changes along the life course, whereas temporal trends across time and cohorts, they are exogenous contextual changes in broader social conditions. So this is why, it's important to allocate the source of variations appropriately for the proper inference. And second, it also relates to the generalizability and replicability of research findings. So in the absence of period and cohort changes, effects, age changes are broadly applicable, right, across individuals in different time and cohorts. But if there are historical and cultural specificity of the findings, then the analysis should account for such exogenous factors to avoid confounding. And as such, it is highly valuable, to do APC analysis for better understanding and identifying the underlying social environmental factors that are amenable for change, for modifications. And so it is important, we now know, but the problem is that it is, in practice, it is difficult to distinguish these effects. Now, they are, in other words, they are often confounded. Now, there are two categories of reasons why that may contribute to such confounding. Here in the introduction, I will focus on the confounding due to inadequate data and study designs. And then later, for the rest of the workshop, I will focus on confounding due to, problematic analytic models and methods. So here, so to understand the problem associated with inadequate data and study designs, I want to show this example. So if you look at this example, that you can understand better the relationship between, in this sort of data, the relationship between the three time dimensions. So this hypothetical data are rated by 4 age groups, age 30 to 39, age 40 to 49, so 10-year age groups from 30 to 69. And the columns are time periods 1970, 80, 90, and 2000. Let's say they are decennial census years. So within this array, each cell then correspond to birth cohorts that are also 10 years apart. This is cohort 1910, 1920. So with the most recent cohort of 1970, they're all lying on the diagonals. Okay. So the problem with using cross-sectional data gathered at one point in time is the confounding of age and cohort changes. So for example, this is again a formal presentation of the cartoon that I showed at the very beginning, right? So let's say we take only one slice of data from 1970, the period being 1970, and then you can immediately see, so in this data where the age 30 is, from cohort 1940, age 40 is from cohort 1930, so on and so forth. So with this, in this one column, it is impossible to tell apart age and cohort. They're completely confounded. They're collinear with each other. So the detection of age and cohort changes can only be achieved when we compare data collected at different points in time, if you add more columns to it, because each period would contain different sets of birth cohorts. If the changes you see are repeated across each time period, then you would be able to tell that it's more because of age-related changes as opposed to cohort, right? And so, but it's impossible to know with only one slice of the data. So similarly, the problem with using a single age group data collected across multiple time periods precludes the distinguishing between period and cohort effects, because within the same age group, period and cohort are completely confounded. And then lastly, the problem with a single cohort longitudinal panel is the confounding of age and period effects. So here, if we take the diagonal of 1940 cohort, so at baseline, they're age 30. In 1970, 10 years later, they aged in together by 10 years, so they're 40 in 1980. So within the cohort, the age and period are the same variable that you cannot tell. Right, so these are very common sorts of problems with these kinds of data. So there are, however, 4 better research designs that I have identified that can help us actually conduct APC analysis and tell us, what is going on with these different effects much better. So this is an abbreviated view of the general data structure that I'll go into, specifically later. But it gives you sort of a glance of what's out there. The first is aggregate population level data, and then usually mortality rates, fertility rates sort of data. And the second is the repeated cross-sectional survey data. It should be added, the data should be replaced by survey instead of, or insert survey in there. The third is the accelerated longitudinal panel. This is not a single, it's multi-wave, multi-cohort data. And then the fourth is the integrated longitudinal panel that puts together multiple longitudinal panel data. And so this is a table, again, this is not to be understood right at this moment, but you can always come back to this slide after we go through today's topics, because it's a summary of each, the characteristics of each research design that we'll talk about, as well as some typical data sets that fall in that design. So it will, be a sort of a summary sheet that you can come back to revisit. And so I would like to point out, I glanced over a lot of things. It is highly recommend getting the highlighted reference here. It's the book that gives a very systematic introduction of all these things I've talked about. Although I have also updated the content of the book by adding the fourth research design, which is based on my most recent research. So I would then quickly want to move to the first topic of the day. Any quick question if you have? I can allow one question. Okay. So yes, Paul.
Saying Ma under confounding table 1, how do we determine the cohorts? C1940, C1930, C1920.
Very quickly, I will do this again in the topic I was just about to tell. Is that so? If you just take the difference between the year of the data, 1970, and the age range. So 1970 minus 30 would be 1940. So this again is actually a quintessential problem that has led to the identification problem, which I'm about to talk about in the next minute. Right? So when I begin to learn how to conduct APC analysis using one or all of these new designs systematically based on a set of guidelines. So part 1 focuses on the conventional linear regression models applied to research design 1 well, this is mostly the earliest population research using APC analysis, and it's unfortunately where most of the field is still stumbled upon as of this point. But hopefully the new topics will bring new light to this body of research. So the overview, I will talk about the research design, and you will see more clearly of the question that we just answered in chat. So how do you, what does the data look like in the age by period tabular rates or table of rates? What the data structure is, the key characteristics, and some examples. And then I will talk about the linear APC models that have been used to fit to this kind of data, and talk about the identification problem and what people have done in the past, and introduce a new estimation method that overcomes the limitations of the previous methods and also gives a step-by-step or 3-step procedure using an example of analysis of cancer mortality rates. So this is a generic form of data structure which we just looked at, but I removed the numbers, but just showed you the general idea. Again, this is a different way of showing the Lexis diagram. So this is representing a rectangular age by time period array of or table of observations, usually as aggregate population level data in terms of rates or proportions. Again, think of mortality rates as a prominent example. So columns correspond to age-specific observations in each year, and rows are observations from each age across years. So as defined by this matrix, age and year are of equal interval lengths. So if you look at CDC data, for example, you oftentimes find 5-year, 10-year specific data. And so age and years are both defined with equal intervals. And when this is the case, the diagonal cells linked by the dashed arrow lines represent cohort. So these dashed lines on the diagonals represent cells, for each cohort, the cohort's lifelines. So and the in this case also each cell, each A by P cell, this square, has a sample size of 1, has 1 age period cohort-specific observation. And this induces the exact linear dependency, which is a fancy way of saying knowing 2 out of the 3 variables, you would know the value of the third. So this is also how I calculated with the example of the birth cohort year. If you know the year of 1970, the age of 30, the cohort is 1940. And so this is a very important observation that's typical, that's characteristic of this kind of data structure. Why I emphasize this, you will see in a minute. Again, also this kind of data use the demographic concept of a synthetic cohort, meaning that they trace the same groups of individuals born from in the same years, that instead of actual birth cohorts collected through longitudinal surveys. So they're synthetic in this sense. Although they're not actual birth cohorts, they're pretty good approximations, especially at the population level. And also, compared to individual survey data, which we'll talk about in the next 2 designs, this design has the advantage of covering a long segment of the lifespan. So some typical data sets or the data sets I'll be using for today's examples are population level rates. Here on the left is the SEERs, the surveillance, epidemiology, and end results SEER data that provide the age-specific cancer incidence rates, where I note as IX, for periods from 1970 to early 2000s. There's a SEER stat software where we can use to download these data. And then linked to these data are the NCHS mortality data for the corresponding cancers. I call them MX. For the approximately same time periods, also can be obtained with SEER stat software online at NCI. So as an example that I got, the data through the website, it's publicly available. I put together this age by time period array of data of cancer mortality rates for US white males. And so as you can see, this kind of maps directly onto the example I just showed here. And then, so we have 14 5-year age groups here, and then 8 5-year time periods. How many birth cohorts do we have without using your fingers to count or eyes? So a simple formula, when you have your A and P values determined, the number of cohort is always A plus P minus 1. So there are 21 10-year birth cohorts lying on the diagonals. Also, but just staring at this table, you learn a lot, about approximate, age-related changes, time periods, birth cohorts. Now, an easier way to look at this, you could do basic descriptive analysis using this table of data, but graphically present them into a two-dimensional plot, either A by P, age by period, or age by cohort. So using the data, well, here also I use the white women's data because they give you better visualization of the distance with larger distances. But essentially, they're the same kinds of data that I just used for men in the previous slide. So here is an overlay of both A by P graph and A by C graph. So the colored lines represent the age-specific lung cancer mortality rates for different periods, from the earliest periods to the most recent periods. And then the sort of dashed lines connect the age-specific rates by birth cohort, from earliest cohort to the most recent cohorts. Right, and so this is interesting, right? This is, showing you a lot of things going on. So we can see how sort of the curve of age-specific lung cancer death rates in any given time period, in any colored lines, cut across a number of birth cohort curves, right? So what this means is that the shape of the age-specific curve is affected simultaneously by varying age effects and varying cohort effects. So disentangling these effects, no matter how good your vision is, disentangling these effects by such visual graphical analysis is just a futile quest, and it requires the use of regression modeling, which is what we're going to do next. It's going to get a little bit algebraic-y. So bear with me if algebra is not your cup of tea. I'll walk you through the main idea. So in addition to descriptive devices, early investigators, mainly sociologists and demographers in the 1970s, they developed regression models. At the time, linear models were all the rage. It just started to enter social sciences. So obviously that's sort of the tool of the pick at the time. So the essence of the regression analysis is, to help us identify and quantify the different sources of variation as regressors on the outcome of interest that are, theorized to be associated with age period cohort effect. So this APC multiple classification or accounting model has been a standard approach to the analysis of research design 1, aka age by period table of rates. And so this model falls into the class of GLM, generalized linear models, and can be written as equation 1, where Yijk indicates the outcome, for instance, mortality rates for ith age group, for the jth time periods, and kth cohort. So those are the rates that live in the cells of this rectangular arrays that live in the A by P cell, right? So F is a simple transformation using either linear, log, or logit link. And mu is the intercept or adjusted mean. Alpha, beta, gamma represent the age, period, and cohort effect coefficients respectively. And then this is a fixed effects GLIM, reparameterization to, the vectors of each parameter vector sums to 0, or alternatively setting one of the indicator variable to be the reference group. They're equivalent. And so this linear model seemingly makes sense, right, to fit the data, suffers, however, from what's called identification problem. This is actually a special case of collinear regressors. So what it means is that the inclusion of completely collinear regressors produce multiple estimators of the unique true effects. So you really end up not being able to get results from this model. So I'll show this problem here in a little bit of greater algebraic detail to show what exactly is the identification problem, but you can skip it if you don't care about it. So the key problem of APC model of equation 1 is shown by, if we rewrite the model, it's the same model into equation 2 in matrix form, where Y is the vector of outcome, X is the design matrix consisting of columns of 1s and 0s, and the B is the parameter vector that includes all the means and the effect coefficient. So if you recall in the LS regression class of the MLE solution to this linear model, B hat, so this is the maximum likelihood estimator of the model parameter. It's the solution to the normal equations, right? Normally it works great. However, in this case of linear model fit to this kind of data, it does not work. The reason being, the linear relationship between these three variables, period being equal to age plus cohort, induces this sort of design matrix X that is singular. A singular design matrix basically means some columns of the X can be linearly combined or summed to produce columns that are identical to other columns. So when this is the case, the X prime X is also singular, and a singular matrix does not have inverse. So the X prime X inverse does not exist. And then when this happens, the normal solution to the solution to the normal equation B hat does not exist, or it's just an infinite set of solutions that fit the model equally well. So you won't be able to really to get any results, that is the one single best solution. So the model identification problem exists without assigning certain additional identifying constraint. So, there have been various conventional solutions to this problem, all of which are, concerned with finding that one additional identifying constraint. So these include reduced one or two factor models. So you don't include all three, you only include two, you don't have the problem. With posing linear constraint coefficients, you can equate two of the coefficients to be equal to free up that 1 degree of freedom needed to for x prime x inverse to exist. This is a very popular method. It's very simple, easy to do. And also there's nonlinear constraints where you could do parametric transformations such as square term, or using proxy variables to replace one of the indicator variables with actually measured characteristics. All of these are also very popular. However, what they share is are two limitations. The first is that the results are highly sensitive to the choice of constraints one used. So that's always undesirable because how do you choose? Depending on the constraints, you get different findings. And then there's a deep mathematical reason behind it, which I don't have time to deal with here, but this is sort of what resulted is this undesirable fact that, analysts are left with, too many choices, but, you don't know which one is the right one. And then also they share the technique they share the purpose of breaking the linear dependency between the three time variables A, P, and C, and thus to identify the model. However, in the context of linear regression models, the problem is inevitable, and so are the limitations. And I will talk more about this later today as well. So in all, they don't work very well. And so now I will now introduce a better estimation method. It's not a new model, it's still an estimator of the linear model. In that context, I introduced the intrinsic estimator, or the IE, that within the linear model framework. So this new method of estimation yields this unique solution to the linear model, and hence identifies the model, and is a unique estimable function of both linear and nonlinear components of the APC model. And compared to previous solutions, it achieves the model identification with minimum assumptions, and it can also be easily estimated using principal component regressions. So the algebraic detail and definitions are given before. It takes a whole day to talk through them, so I don't think it's worth it. But I will just talk about the intuition of, behind the algebra. So the reason why the identifying constraint used by this new estimator is better, or better justified, it stems from a mathematical fact that any other constraint any other constraint allows the design matrix X to have some non-zero impact on the outcome Y. So what does that mean? So the design matrix is fixed once you have your data. The design matrix is defined by the dimension of the data, is defined by the numbers of age groups you have, the number of periods you have. And hence, it does not have anything to do with the random variation in your outcome Y. So, to realizing this fact that a reasonable constraint should somehow remove the impact of the data structure, the dimension of the data on the outcome Y. So when you do that, you come up with, this is the essence of IE. So the IE does remove the influence of design matrix X on the coefficient estimates, whereas we have proof that other constraints that are different than IE somehow allow that X to have a role in the estimates of the variations in Y. And therefore, the identifying constraint of the IE is better justified. Let me know if you don't understand anything I was just saying. So using this better constraint produces an estimator that has desirable statistical properties, including estimability. By estimability, it guarantees unbiasedness and also has relative efficiency and asymptotic consistency compared to the other constraint estimators. And so most importantly for users, for our, from the user's perspective, the coefficient estimates are easily interpretable compared to some of the nonlinear constraints used in biostatistics literature. So exactly how does it work? So I'll go through a 3-step procedure just to show how to, thread through everything I've talked about as of now in a real example. So step 1 always begins with knowing the data. Knowing the data, doing descriptive analysis. And I prefer graphics because they somehow, ease the, understanding of the data patterns compared to big tables of rates. And step 2 is do some model fitting comparison. And so what these 2 steps are aiming to do is it has 2 objectives. First is to provide us some qualitative understanding of patterns of age, period, or cohort variations, or 2-way, either age by period or age by cohort variations. And then they can help us understand, or determine whether the data are sufficiently well described by any single factor or 2-way combinations of the A, P, and C dimensions, or it is actually absolutely necessary to include all 3. And step 3 is to estimate the final model based on the best fitting, to estimate the model based on the best fitting, model. So if the first 2 steps lead to the conclusion that the full APC model is the best model, then use the IE. So as an example, I will use the cancer mortality data that I just showed in the previous table, which is also available in chapter 6 of the book to do this linear APC-IE analysis of US cancer mortality trends. So step 1, descriptive graphical analysis. So this, again, is a graphical presentation of all the data tables that we have. Again, here we're focusing on lung cancer rates. On the left is incident rates. On the right is mortality rates. And then we have the rates by race and sex simultaneously. So we have, these partition, individual graphs for each subgroup population. And then the time periods, while they are, as what I showed in the original data, 5-year age rates by 5-year time periods. Here I, aggregated the periods into 4 decades, just in the interest of space and also better visualization because they are separated more. They're more delineated by decades, and you can see some pretty big trends, right? Where the more recent decades, as indicated by the blue lines, are much elevated for most of the subgroups here. And so using this as sort of the first take of the analysis, you get some initial qualitative sort of understanding. So age patterns show continuous increases before old age and leveled off in old age. Period changes show large increases particularly in the most recent 10 years. And then there's also potentially cohort variation where you can tell the existence, although not quantitatively, the existence of cohort variation when you see the age-specific curves across time periods that are not parallel. So in a way, non-parallelism of age curves across time periods indicates an age by period interaction, and it's an alternative interpretation of cohort effects. So, what the graphs show that, you could go back and see, large, clear signs of non-parallelism across these period-specific age, curves. So you can tell there's something going on with cohort variation. They somehow show increases, but let's see if we move on, if we get the same results after we fit the models. So step 2, model fitting and comparison. So after step 1, we somehow know that, maybe all 3 factors are at work, but, we need to put this idea to test by fitting models. And then, so step 2 will fit the models to find which factors are actually, they actually matter. So we move one step closer to pinpoint the relative importance of these effects in explaining the observed rates using linear regression models. So the purpose here is to fit different models to find out which model best summarizes the data. We can compare measures of model fit in various ways for different models, R-square for linear models. Most often we use likelihood ratio statistics to get, or deviance statistics to get penalized functions for generalized linear models using AIC or BIC. And then exactly what models we fit, we can first estimate reduced models. By reduced models, I mean single factor model, just gross age, gross period, gross cohort models, or reduced 2-factor models, AP, AC, and PC. Now, in studies of human health, we just talked about how age is important. So pretty much it's, I have seen across the board through many applications that models that do not include age effects are not good fitting models. So you can somehow narrow down the choice of reduced models to those that include age factors for sure. And then lastly, we can fit full APC models. Now, how do you say this is chicken and egg? So I have to use something to identify the model. So how do I actually estimate a full APC model without the third step? So the interesting factor is that if you use the constraints that just identify the model, meaning that you just free up that 1 degree of freedom, it's called just identified models. No matter what constraint you use, you get the same model fit. Because in model fit comparison, we only care about model fit. It does not matter which constraint you use. They give you the same model fit. But it will tell you the difference between a full model versus the reduced model. So bearing that in mind, here are the results of BICS statistics for the log linear model fit to the lung cancer incidence rates on the left and mortality rates on the right. So we compare 4 reduced models here, A, AP, AC, and APC. The statistics in bold indicate the best fitting model because the smallest BIC is the model of choice. So we can see for all groups except for 1, other females, the best fitting models are all the full 3-factor APC models. So if the first 2 steps suggest that not, if only 1 or 2 of the APC dimensions is operative, then the analysis can proceed with a reduced model that does not have the identification problem. It's the best case scenario. If, however, these analyses suggest that all 3 factors are at work, then we need to proceed to step 3 for the full model estimation using the IE. And here's yeah, Paul.
The question is, why is it not sufficient to conceptualize cohort effects as age by period interactions?
It's not insufficient. It's an alternative interpretation. They're statistically identical. Not statistically. They're substantively the same phenomena. Is statistically equivalent if you replace cohort membership with age by period interactions. They're equivalent. But cohort membership, has somewhat more parsimonious kind of, as a more parsimonious indicator. And sometimes people like to attach other substantive meanings to cohort membership other than the statistical fact that produced it. Age by cohort interaction is what's actually driving the cohort effect, but cohort effect somehow has its own kind of life if you just use cohort instead. But they're statistically identical. Good question. And so this is a messy slide of computation algorithm. Again, if you like to have fun coding, with whatever software of your choice. This is the blueprint that basically the first 4 steps are principal component regression, and the last step, step 5, uses inverse orthonormal transformation of the coefficient estimates of the PCR back to the original space of A, P, and C coordinates. So this ensures the coefficients to be directly interpretable as A, P, and C effects. I provided here in case you do want to do your own programming. Some of my students, did that, with their own. So, but I did work with econometrician earlier on who likes Stata to, we did we added a file to Stata that you could just, use directly here if you're a Stata user. So first what you do is to install the ado file. This is the command. And then, so let's say the sample codes for IE analysis of the white female lung cancer mortality data that I just showed. You want to use the model to estimate it. This is what you do. So you first read the data in. If it's in text file, whatever file, it's okay. It's just an example. And then the command is APC-IE. If you have used GLM in Stata, this is exactly the same syntax structure. And you plug in your own variable. Here, the exposure means the denominator of the rates. The rates is the ratio of number of events divided by population exposure. So here, in order to use the Stata command, you somehow need to have the exposure data separately in the matrix. And then the death, is the death counts is its own data, exposure is its own data instead of the combined rates data. So this is the death counts variable. This is the population exposure variable. Families, Poisson, log link, age, period, cohort, plugging your own variable name, and then you get the results. An example, the output's long, so I put an example of fitting the model to female general mortality from a previous publication on my website. So you could take a look at that and see, try to, if you want to replicate. An R&S program also exists. It's a little more cumbersome the way it has been written, but like I said, the computational algorithm that I showed earlier should enable you to write your own codes. So there are some source codes, existing source codes that you could upload. Dr. Fu wrote those codes and he would not like me to distribute them openly, so he would prefer to be emailed, and you can also email me directly afterwards if you would like to use this. I can send you them individually. And then the codes to actually fit the model, again, you input data sets separately for rates and exposures. It's a little different from Stata. Stata use death counts and exposure, the ratio of which are rates. Here, for our codes that are written here, rates are, already, its own matrix, and then you have exposures as well. And so you read them in as matrix. This is the rates, this is exposure, and then run the model using APC Ridge, RDGSE, and then all the specifications are written here, and then you can fit it. You may prefer writing your own codes, but I'm just showing here. So after you do this, run this. Also, SAS codes for IE has not been written yet, so you're more than welcome to do your own thing if you have the algorithm written out. So after you get the output, right, how do you present the results? So it's the same as any GLM model applications. You get the point and interval estimates of effect coefficients estimated from these models, and they're interpreted as they supplement results from your step 1 descriptive analysis. What's different here is that it offers additional insights on the distinct sources of change. Like I said, descriptive analyses are useful, but they are only qualitative. So the actual quantitative determination of these effects will have to rely on regression. So this is what this does. So you get estimates of the distinct sources of change across coefficients of, from coefficients of successive categories within the A, P, and C classifications that show the net trends of outcome along the 3 dimensions. So I put them again on graphs, which I'm a visual person. So this is all the log coefficients from the results that you could plot. They are the estimates that tell you the net age, period, and cohort effects not confounded by each other. So these are the sort of the beauty and parsimony of the model estimates. And so you could learn, well, age effects look very much like before, as they should. Period effects are surprisingly flat and small and maybe slightly upward trending. The star here is, again, the large cohort changes. There's some initial increase or leveling earlier cohorts, but subsequently all the cohorts experience substantial declines. So this leads to the final set of results where we see age effects that suggest the instance suggest the influence of cancer biology and human mortality trends. Cohort declines, they suggest real progress in cancer prevention and control and improved survival, as do many other leading causes of death of the US population. Most interesting here is that standard models of period changes that do not consider cohort changes are misspecified. You can see this by, I just mentioned it before, period effects are small relatively when both age and cohort effects are simultaneously controlled and unconfounded. And mortality declines that have been most, previously that were attributed to period changes actually are captured or attributed to cohort rather than period. And then the slightly increasing period trends are also alarming and interesting. They could be related to actual increases in exposures to carcinogens, or could be due to some other demographic mechanisms. So these are all questions for future research. Yes.
Do you say more about
That's a very good question. Let me go back to, if I can, it will take forever. Initial, do I show all the slides at once? Oh, there you go. So continuous large cohort declines in human mortality all the way until 20th century have been largely found also for cause-specific mortality such as cancer. And then the leading hypothesis underlying this phenomenon is called cohort morbidity phenotype hypothesis, postulated by Finch and Crimmins. So what it says is that early life environment changes in more recent cohorts, such as reduced infection, chronic inflammation, increased access to nutrition, they have all boosted human physiological reserve that can have enduring impacts on surviving members of the cohorts well into midlife or into old age. And so this, again, cancer is mostly a disease of the immune system, inflammaging, so reduced infection and inflammation and better access to nutrition, barring obesity, of course, is somehow behind the increased survival for more recent cohorts from cancer-related mortality. You're welcome. So, am I over time for the first section? So we have learned a lot, by running through the 3-step procedure, and then you're welcome to, be creative yourself by, playing with your data various ways. So key references I would like to include that provide a lot of additional information, as well as applications to US mortality data, and race-specific, sex and race disparities in mortality in more recent couple of publications. They're very good sources for continuing future research. So I would like to take a break here and maybe a couple more questions before we, come back at 10:30 for the next part. Any other questions?